In the last video, we remarked briefly on the utility of a standard set of potentials. And in this video, we're going to clarify what exactly we mean and introduce the standard reduction potentials and the electrochemical series, the series of half cells from most reducing to least reducing. The standard electrode is known as the standard hydrogen electrode, and the standard half cell potentials that we use are reductions. What we do to measure all these potentials is take the standard hydrogen electrode and hook up to it a huge variety of cathode half cells such that the She acts as the anode. So the She is transferring electrons out to these various cathode type half cells, and we're measuring the potential associated with this for each half cell She combination. So there's a reduction potential here, there's a reduction potential here, and a reduction potential here for these various half cells, and we can generate a huge list of these so-called standard reduction potentials by just connecting cathodes up to the She and measuring the associated potential. To reveal how and why this works, I want to take a look at three related galvanic cells. In the first, we have copper immersed in a solution of copper 2+, and that's connected to a half cell containing magnesium metal immersed in a solution of magnesium 2+. And these are both, by the way, under standard conditions. So this is our first half cell, and assume that there's a salt bridge between these two as well, so that we've got all the necessary components of a galvanic cell. Second cell I want to build uses copper again as the cathode, a piece of copper metal immersed in a copper 2+ solution, but changes up the anode to use, instead of magnesium, zinc metal immersed in a solution of zinc 2+. There's a salt bridge between these, and we connect the two with the wire so that we can measure the voltage across this cell. Finally, I want to return to using magnesium metal and Mg2+ as the anode, and change up the cathode now to be the zinc metal in a zinc 2+ solution. Again, connecting these with the salt bridge and connecting the two pieces of metal with the wire so that we can measure the voltage across this cell. So these three cells are related. You'll notice that magnesium is serving as the anode in two of them, to a copper cathode and to a zinc cathode, and there's a zinc copper cell as well. Check out the measured Ecell values for these three cells. For the magnesium copper cell, the measured cell voltage is positive 2.71 volts. For the magnesium to zinc cell, the voltage is positive 1.61 volts. And for the zinc to copper cell, the voltage is 1.10 volts. Why is this interesting? Because 1.61 volts from magnesium to zinc plus 1.10 volts from zinc to copper gives us the voltage of the cell from magnesium to copper, 2.71 volts. The E cells appear to be additive. If we think of the magnesium half cell as electrode 1, the zinc half cell as electrode 2, and the copper half cell as electrode 3, what we're concluding here is an almost Hess's law-like conclusion that the cell voltage associated with the 1 to 2 cell plus the voltage associated with the 2 to 3 cell is equal to the voltage of the 1 to 3 cell. This is a pretty remarkable result, and it shows essentially that E cells obey Hess's law. E cell is a state function for a particular half cell, and it obeys Hess's law. We can take any route from electrode 1 to electrode 3, and we'll still get the cell voltage of 2.71 volts through an intermediate zinc electrode, and we'd still get 2.71 volts. So the cell voltages are additive, and actually, given the relationship we've previously seen between E cell and delta G, namely that E cell is equal to negative delta G divided by N times F, this shouldn't be too surprising because this obeys Hess's law, so the cell voltages should also obey Hess's law. So just like we did for delta G's in defining standard free energies of formation, for example, we can define a standard cell voltage for a half cell, the electrochemical potential of a half cell connected to a standard electrode, which is going to be the standard hydrogen electrode. Remember that the idea when we did this for enthalpy and enthalpies of formation was that we defined the enthalpies of all of the elements to be 0. That meant that we could take the reactants back to their elements, and there was some negative change in enthalpy associated with that of formation, and then convert those elements back to products, and there was some positive enthalpy change of formation associated with that. We can do something analogous with a galvanic cell. We imagine a galvanic cell as an anode, which donates electrons to a cathode. If our goal is to calculate Ecell for this cell involving the anode and the cathode, there's no reason we have to send the electrons directly from the anode to the cathode. Ecell is a state function, so we can send the electrons wherever we want en route from the anode to the cathode. Our idea then is to define a standard electrode through which we send the electrons in a galvanic cell to help standardize calculation of cell voltages, and this is the standard hydrogen electrode. The idea is, instead of sending electrons directly from the anode to the cathode, send electrons from the anode to the standard hydrogen electrode first, and then send those electrons from the standard hydrogen electrode back to the cathode. Because we need to make a conventional decision, which is a relatively arbitrary decision, about the signs of these cell voltages, we decide that the standard potentials are reduction potentials. And so the process in which electrons are traveling from the She to the cathode, which is a reduction, is associated with the positive reduction potential. Now the number itself may be negative or positive, but the point is we don't multiply by -1 here, since the electrons going from the She to the cathode is a reductive process at the cathode. Sending electrons from the anode to the She involves oxidation at the anode, and the potential associated with that is negative ER for the anode. Why is this negative? Since this is an oxidation of the anode, and by convention, actually, the reduction potentials are for the process of sending electrons from the She back to the anode. So we define the She as having a standard reduction potential of 0.0 volts, just like we defined the enthalpies of the elements equal to 0 in the enthalpy of formation case. You can see that when we calculate a cell voltage, we do that by starting with the reduction potential for the half reaction occurring at the cathode, which is the reduction, and we subtract from that the reduction potential for the reverse of the reaction that's happening at the anode. It's an oxidation in reality, but since the standard potentials are reductions, we use a negative sign. The reason we use a negative sign here is conceptually exactly the same as why we use a negative sign in calculating delta H of reaction as the sum of product enthalpies of formation minus the sum of reactant enthalpies of formation. To clarify this cell voltage equation, you may also see this written as E circle R for the cathode, which will be positive, plus a negative or minus E circle R for the anode. Let's talk a little bit more about the standard hydrogen electrode. There's a really nice figure of what's going on in the standard hydrogen electrode here. The reaction itself involves the oxidation of H2 in its gaseous state to form two protons, two aqueous or solvated protons, and two electrons. It's an oxidation half reaction since by convention we think of the She as the anode and our electrode of interest as the cathode, so we're measuring a reduction potential. The standard reduction potential for the proton, which is the potential associated with two aqueous protons accepting two electrons to form H2 gas, is defined as 0.0 volts. This is part of that convention, and it's necessary to give us a standard for the cell voltage, 0.0 volts for the reduction of H+. And in this experiment, as we've mentioned several times, the She is always considered the anode. Oxidation of H2 by the cathode half cell may be spontaneous or it may not. That's why the standard reduction potential can be either positive, in which case that oxidation is spontaneous, or negative, in which case that oxidation is not spontaneous, and in fact, the reduction of protons is spontaneous. The reverse direction is spontaneous. We want to develop a good intuition for what a positive standard reduction potential means and what a negative standard reduction potential means. So on the next slide, I've listed a ton of measured reduction potentials. To measure these, we connect each of these half cells, a half cell in which these half reactions occur, to the standard hydrogen electrode, and then we measure the potential of that half cell relative to the standard hydrogen electrode. Positive reduction potential means that reduction of the species on the left-hand side of the half reaction is spontaneous. So one of the most spontaneous reduction potentials is the reduction of F2. F2 plus 2 electrons goes to 2F minus. Why is this so positive? Why is the reduction potential for this half cell much greater than 0? Well, fluorine is a very electronegative element. It wants to accept electrons. And if we think of the process of reduction as accepting electrons, which at the deepest level it really is, then it makes sense that this should be pretty spontaneous relative to, say, the reduction of H+. F2 really wants to accept electrons, and it does so spontaneously when those electrons are donated from a molecule of H2. Negative reduction potential means the opposite. Oxidation of the right-hand species is spontaneous. On the other end of the electrochemical series, we've got lithium plus accepting an electron to form lithium metal. And what the very negative reduction potential for this half cell shows us is that, in fact, this reaction as written is non-spontaneous relative to the standard hydrogen electrode. When you hook up a lithium plus half cell to the standard hydrogen electrode, in fact, this reaction wants to go in the other direction. Lithium metal wants to give up an electron to form lithium plus and the electron. Does this make sense? Well, it should. Lithium plus is a relatively stable cation. Lithium is a metal on the far left-hand side of the periodic table, and we rarely see lithium 0 in any sort of reaction. That's because it spontaneously wants to give up its electron really badly to form a cation with a full valence shell and all that good stuff. So we can use electronegativity to rationalize this series to a large degree. Note also that every redox reaction involves reduction and oxidation, and this is at the heart of the formula we use to calculate standard cell voltage. It's the positive reduction potential for the cathode half cell minus the reduction potential of the anode half cell. Since oxidation is occurring at the anode, we need this negative sign for the voltage associated with the opposite of reduction, oxidation.